Okay, power flow analysis. So on Wednesday, I briefly talked about the importance and assumptions of power flow analysis. So the assumptions include the steady state conditions for the system, or at least the voltage and current phasors need to be well defined. The system usually is considered a balanced network for a three-phase AC system, such that we can use a single-phase network to do the calculations. And substations are called buses, which means even they can have very flat layout, but it will be treated as a node or a bus connecting branches to other substations. Both transmission lines and transformers are treated as branches. So the model will be a per unit model. So there will be a common power base, MVA base, such as 100 MVA at the power base, and different lines or equipment depending on their voltage, nominal voltage. So they can use respective voltage bases at their bases. So finally, the system will have per unit value everywhere. So for the impedance or admittance, though they will be represented in per unit values, and voltage will be always around 1. So if you consider operating a system to maintain the voltage within maybe 5% deviation, so the per unit value everywhere will be roughly from 0.95 to 1.05. So for any substation, if the calculation tell the active power is 1 per unit, basically it means 100 megawatt. If 1 per unit for Q, it will means 100 megawatt, right? So just make a calculation easier. I brought this problem back, which was from the section number 2. It is a power flow problem, it's literally speaking, but it's based on a very strong assumption, such as the voltage everywhere will be same, such as we can have very useful formula to help us to calculate power flow, which is the Q everywhere will be the same and the P everywhere will be opposite. But when we come to a more general problem, even we take the similar topology or similar complexity for the network, at each bus, we may know some variables, but we still need to solve the other variables. For instance, at this substation, we know the active power 0.5 per unit, which means 15 megawatt power if we use 100 MV as a base. We know voltage magnitude is 1.05, which is 5% higher than the nominal voltage. But we still need to solve Q2, which is the reactive power, and also we also need to know the angle. That's for bus 2. Definitely for bus 4, for example, we know P and Q, but we don't know the voltage and angle. Okay, so each substation we need to give some values, and we still have to determine the other values. So that's a more general problem for power flow. Okay, so at the end of the lecture on Wednesday, we try to standardize the model for each bus, such as we can, no matter whether the bus is connected to a source, a load, or nothing, we can always convert to the same structure. And we put those structures together, we can write down the equation, right? We really don't want to just study each individual bus one by one. Just think about if you want to solve power flow for, let's see, the eastern connection for the entire North American system on the eastern side. So that system, even you only just study the voltage levels about 100 kV, the complexity of model is like 100,000 buses. Okay, probably 100 to 200,000 branches. are you going to apply the Kirchhoff current law, voltage law to each individual bus or branch, then try to solve the Prof law? That's definitely, theoretically speaking, that's a solution, but it's not very practical. So the idea we have here to solve the Prof law problem for any complex system is to have a standardized model for each bus or each branch. Then, okay, so even the bus doesn't have a source, which is still a treat the bus having a source. Okay, we just gave it a very standard model. And for this very standard model, we know what equation we can write down. Okay, we just write down the equation for every such bus or branch. So if the actual bus meets some source or some value, we just simply give it 0. So that will be very easy to write down all the equations and put into some matrix form. Then we can solve the problem. So that's our idea. So that's why we need to find a very standard model for each bus here. Okay, now let's just take the bus 1 from the previous very simple system. So that bus 1 has a single source. It can be a generator. If it's generator, it will have EMF, which is E1, internal voltage, connected to this bus through a readance. So this readance for generator will be a synchronous readance. So for this case, we ignore the armature resistance, but if you want, you can add armature resistance. Okay, so then the source is connected to the bus 1, and the bus 1 will have a different voltage V1. And then the bus 1 can be connected to maybe 2 of the other buses. One is bus 2 and the other is bus 3. So it will have current from 1 to 2 and current from 1 to 3. And each branch will have a impedance or readance. For this case, we assume the line to be lossless, so you don't consider resistance, so it will have inductive readance. Okay, so for each branch, you can definitely calculate the reciprocal of the impedance. It will give you admittance. So this is pretty typical bus. For this bus, we'll find the standard model to represent this bus. So the idea is the first step is just apply the Kirchhoff current law, not voltage law, Kirchhoff current law to this bus. We study the current injection into this bus and leaving this bus. So that have to be equal. That's a Kirchhoff current law. So we'll just go ahead to write this equation. The left-hand side will be the currents from this bus going to the neighbors. There are 2 neighbors, bus 2 and bus 3. The right-hand side will be current coming into this bus from the source. Because of the voltage drop along the synchronous readance, which is from E1 to V1, multiplied by the admittance of this internal impedance. Okay, and so next we just convert the first item, which is equal to the EMF E1 multiplied by the synchronous admittance. We call this one as current injection. So we just convert this voltage source into a current source. We call it I1. I1 doesn't really exist in the original system, but it's just equivalent constant current from this source. So if this source has EMF E1 constant, synchronous impedance C10 also constant, then this I1 will be constant. Okay, so this conversion doesn't cause any error. It just is accurate conversion from the voltage source to the current source. So this will be we can treat this one as our standard model for every bus. So for any bus, if that bus doesn't have source, we just simply treat this one to be 0, right? So if it does have a source, we just give it I1. Then we can write down a standard equation. Left-hand side will be the current from this current source, and right-hand side will be the current leaving from this current source, from this bus. So those two items are pretty clear. Those are the currents going to two neighbors. And the first item on the right-hand side is actually is equal to the bus voltage multiplied by the admittance to the source. Okay, but in our standard model, which indicate also the current leaving from this bus, because that is exactly this current. So left-hand side will be the current from this constant current source. The right-hand side will be current leaving from that bus. The first item will be the current going to the ground. So we treat the ground also as a bus, and we give it number 0. So that's why admittance we call it Y10. Y10 means just bus 1 to bus 0. And the other admittance will be numbered by a 2 subscript. The first one will be this bus, and the second will be the 2 bus. Okay, so we can apply this standard model to any other buses. So each bus will have a constant current source. If this is bus I, so we call the current II. Buses will be the VI, and the other buses will have voltage from V1, V2, V3 until Vn. And if this is a source, it will have internal impedance. So that will become admittance to the ground. So for this standard model, we'll have the equation left-hand side will be this constant current, and right-hand side will be the current going to neighbors and also the ground. So first item is the current going to the ground, and the other item will be the currents going to the neighbors. Okay, so when I say neighbors, I just consider any other buses. But what if like between the bus 1 and the bus 2, there's really no transmission line. There's no branch, no transmission line, no transformer. That's fine. So like for instance, let's say if between bus N, there's really no transmission line. There's no physical connection. We simply just let this Y be 0. Okay, we still keep this same structure. We don't worry about which branch really exists or not when we determine this standard model. We just leave the task determine the values of each individual Y for the next step. So this step we just determine the standard model, and next step will determine the actual value for each Y. Okay, so even some branch may exist at the beginning. When we consider some contingency, you can open the line. If you open the line, that Y will become 0. So which means under normal condition, you may have all Ys, but if some contingency happen, that can make any Y to be 0. Okay, so which means this standard model is applied to both normal condition and abnormal condition. You may wonder why we use the Kirchhoff current law at the first step, not the Kirchhoff voltage law. Yeah, so think about it. If you have a power system with N buses, M branches, if you use Kirchhoff current law, the first step is so you need to convert each voltage source to current source, and you are going to generate such equation totally only just such N equations, right? If you have N buses, you apply the Kirchhoff current law to each bus, you'll have N such equations. If you want to apply the Kirchhoff voltage law to create another standard model, the standard model will be about each branch. You'll have M such equations. Theoretically speaking, the two will basically about the same, right? It's still about system. As long as you have standard equation, that'll be okay. But the convenience of using the Kirchhoff current law to each bus is you don't change the number of equations because those substations are there. Unless you remove that substation, you do some planning study, you get rid of the substation or split it into 2, you are going to change the number of equations. even you open a line, open 2 lines, 3 lines, it doesn't change the number of equations. So that's why using this standard model is very convenient for contingency analysis. Any question? All right, so if that does make sense, let's move on. Okay, so for such equation, it will have, for n-bar system, each equation will have n terms. The first term is this bar is going to the ground. So this one is going to the ground. And the remaining term totally will be n-1, because for each bar, they will have n-1 neighbors at the most. Okay, so totally will have n items in each equation. Now let's come back to that simple system. So it has 4 buses. We just number it from those buses from 1, 2, 3 to 4. Each branch it has impedance. So let's first convert this network to our to another network using the standard model. First, we want to change. We don't change anything for each branch. We just take the admittance instead of impedance. So, for instance, for this one, the impedance 0.5. Admittance will be 1 over impedance 0.2J. The inverse will be 1 over 0.2J, right? So will be negative. Will be negative 5J. So that's admittance, but that's about the same admittance, same line. So we'll do this one for every branch. And for the original system, it has 2 voltage sources. So in the equivalent system, we'll have 2 current sources. So next, we will apply the standard, the equation for each bus. So we're going to have 4 equations. So which will be those 4 equations. So on the left-hand side of each equation, so there will be current, right? Only the top 2 current are non-zero. I3 and I4 will be 0 because there's really no current, which means if you trade, there's maybe another current source going to bus 3 and bus 4, but those actually 0. Okay. So basically, you only have 2 non-zero current on the left-hand side. On the right-hand side, each equation will have how many items? It will have 4 items. The first item will be the local voltage of that bus to the ground, multiplied by the admittance to the ground. And the next n-1 items, which means for this case will be 3 items, will be the voltage difference for each branch multiplied by the admittance to that neighbor. So in this case, let's use bus 1 as an example. So it only have totally 3 non-zero items. So this one is the local voltage multiplied by admittance to the ground. And this is from bus 1 to bus 2 because there's a real physical connection. So, and the voltage difference multiplied by this admittance. And the next item will be the voltage difference between bus 1 and bus 3 because there's also another physical connection multiplied by the admittance, which is this negative 5J. But from bus 1 to bus 4, there's really no connection. So you can still write down this item, the voltage from 1 to 4, but admittance 0, which means you can ignore this item. So similarly for other equations, you also have some non-zero items, some 0 item. For 0, you can just ignore them. Okay. but we have a standard equation. So next one, we want to do some simplification based on those equations. So what I did is let's use the first equation as example. So this first equation involves three voltages: is V1, V2, V3. That's a three buses connected or involve this bus 1. Okay, it doesn't. It has no relationship with bus 4. So there will be a 3 voltage. We just create 3 items based on those 3 voltages. And the first for the V1, it will involve 3 admittances. The first one is local to the ground. The second is to bus 2. The third one will bus 3. So basically, we collect this value, and this value. So those 3 will go into the first item. So they all relate bus 1 to itself and also to the neighbors. And we also see, but we still miss another 2 items, right? So each one the coefficient will be admittance with a negative sign. So that indicates the remaining 2 items, talking about the connection between this bus 1 to bus 3, bus 2 or bus 3. Similarly, we can do such simplification for other buses. So we'll have such structure. So this structure is even better in the regional, because regional one, you have on the right-hand side of each equation, you have 4 items. And the first item, each item represents the voltage difference, right? The first item is from the voltage to the ground. And each following item will represent the voltage difference between this bus and to the neighbors. But in the new format, the right-hand side, we have a number of items as many as how many buses is connected to. Okay, so which means every item will be pretty standard. It means sum the meetings multiply just a single voltage. It's not the voltage difference. So this one is even better. If we generalize the second form, it will meet this equation. So each equation will have 2 types of the items on the right-hand side. The first one will be, so if we're talking about the equation about II, bus I. So the first item, which is this one, that one will have a general form, which is the voltage, the local voltage, VI, multiplied by the summation of all the admittances for branches connecting this bus. That's the first one. And the following item will be summation of many individual the product. Each product is actually the voltage not at this bus, like Vj, and multiplied by the admittance connecting bus J to bus I. And also there's a negative sign. So if you can move this not sign inside. So the second type of item is the voltage of any other bus multiplied by a negative admittance from that bus to this bus. So this is second type of standard form. We don't want to memorize this equation. Actually, you need to memorize this equation anyway. Later, if you want to solve problem, but for now, we want to find an even simpler form for this second type of equation. Let's just go ahead to give it the standard form. Okay, so the second form will have it can be standardized by the following equation. On the left-hand side, we have a current injection from each source. So if there's no source, that current injection will be 0. But if there's a source, that will be non-zero. And the right-hand side, we have items as many as a number of buses. So for the system, we have 4 buses. The right-hand side of each equation will have 4 items. So each item is just simply that each bus, the voltage at each bus multiplied by a coefficient. We call it a capital Y. And the subscript will be from this bus to that bus. Okay. So which means the first item will be Y11. Y11 means just admittance, some equivalent admittance from bus 1 to bus 1. And second item will capital Y12 will be the equivalent admittance from bus 1 to bus 2. So you can just repeat for everyone. So this is even better standard, but for this case, we know any items with in the magenta color will be 0, right? Those items will be missing. But when you create this standard equation, you can assume they will be there, the whole deposition. Okay, so for this third form, we can write down very simple equation, just single equation for each bus. And we can even give it like a matrix representation. So left-hand side will be a vector of current, including the injection from all buses. Right-hand side will be there's a square matrix. We call it capital Y bus. This is we call bus admittance matrix. And then multiplied by a column. The column will be a current vector. And this form is very useful for computer to solve a problem, right? And but how do we determine the value of the capital Y? We need to just compare the bottom equation to that more complex equation. Then we can know how to figure out the value for each capital Y. They're related to those lowercase y's. Any question? Okay, so they have to be equal. Okay, let's take a closer look into this bus admittance matrix, capital Y bus. So I color the diagonal element in red because from previous slides, we know that each diagonal element will take the value in those parentheses in each line. So which is like summation of the admittance to the ground and to all the neighbors. And off diagonal elements is simple, pretty simple. Like for instance, in this off diagonal element, basically just the capital Y13 is equal to negative lowercase y13. It's just opposite value of the actual admittance. Okay, so we can keep this equation as the definition of those capital Y. All right, so we put this standard structure for each bus here, just for comparison. We need to figure out how to, for any type of bus, how to construct those lowercase y then the capital Y's. Okay, so let's assume this is bus I. It has current injection II and going to other MS1 buses. So each branch can be either a transmission line or transformer. If it's a transmission line, so we'll take this pi model. If it's a short line, we only need to model the impedance. Right? We don't even need to consider admittance to the ground or capacitance to the ground. For medium line, we can take this pi model. So the impedance here will be the actual line impedance. And admittance to the ground will be the half of depend on the half of the total capacitance. So we split the total capacitance C into half. And each half multiplied by j omega will become the admittance to the ground. So we put on each end. If it's a long transmission line, we need to utilize that hyperbolic function, right, to convert the actual z and y to the z prime and y prime. So that's what we need. So anyway, we will have a pi model for each line. If you have a transformer can also have a pi model. If it's not phase shifting transformer, the transformer only just represents can be represented by some internal reactance. So that is similar to a short line. And we'll talk about that later. But anyway, so for each branch, we can have pi model. So when we create this pi model, for the impedance, we change it to the admittance and we give it to this branch. So when we, in our standard network, we have Y admittance between this bus I to bus N. And that value will take the reciprocal value of this impedance. If you have two branches, two physical branches going to the same bus, let's say you have another line also connecting bus I to bus N. So you have two pi models. So you have two Z's. You have one Z IN, you have another Z IN. So those two Z's, for each one, you need to change it to admittance. You add them together. So that gives you the total admittance. So in our final bus admittance matrix, we only just have a single Y representing the connection. Even if you have multiple branches, you have to combine them to the total admittance. Okay. How are we going to deal with those two items? Those two items for long transmission line, they come from the capacitance. So total line have the total capacitance, right? So you split the total capacitance into half. Then multiply this one by j omega. So this one will be the half of the admittance. So this will be exactly that value. So this item will go to yi0, and the other one will go to the other item. So for this case, if we were discussing on bus N, so this one will go to yn0, right? So for the pi model, the total admittance is split into two halves, and the first half going to the left, the other half going to the right. Okay. Similarly, for each branch, let's say for example, this branch, they also have the impedance. So impedance will stay here, and it will also have admittance to the ground. The first half, the left half, will go to the same one, the same y0. And the other half will go to, the other half will become, if we take this naming convention, that'll be the y20, right? Yeah. Okay. Finally, we determine the how to calculate for this standard model. So yi0 here will combine many things. The first item is actual impedance to the ground. If it has a source, if it has a source, this one will from the synchronous reactance, the synchronous impedance of this source. And then it also combine many items. So each one will be half of the admittance of each branch. So if this bus is connected to many, let's say five other substations, so it will have at least 6 items. The first item is actually the impedance to the ground, and the other item will be the from the admittance from the other to the other 5 substations. Okay, so I-bus here is the current injections by the external current sources. Those current sources will be from the voltage, from generators or other type of the sources of voltage. V-bus will be the vector of bus voltages related to relative to a reference. So here, if we define the ground to be the voltage 0, so V-bus, each item in the V-bus will be the actual voltage relative to the ground. Y-bus here is basically this square matrix. We call it bus admittance matrix. Usually this matrix is symmetric. When I say usually, there's some condition, under some specific condition, this one may not be symmetric, but most of cases this will be symmetric. Because from this the definition you see, if capital Y12 means admittance between bus 1 to bus 2, and capital Y21 will be the same admittance, right, for transmission lines. The definition of the diagonal element will be the summation of all the admittances connecting this bus, including the ground. So how many items? So there will be totally n. For n bus system, this summation will consider the first item is the admittance to the ground, and then the remaining n-1 item will be admittance between this bus to the neighbors, to one of the neighbor. So that's why there are totally n such items. For instance, for capital Y11, it will be a lowercase y10 and then y12 and 113. So this 0 means there's no such item which is like lowercase y11. Okay, there's no such thing. And the total number is total number non-zero item will you need to consider totally n. But if there's no physical connection to bus 4 and bus 5, so those items will be 0. Use that the previous slides, use that system as example. The Y22 can be like Y20 to the ground, and 21 and 23. There's no such thing called Y22. Off diagonal elements. So they are called mutual admittances or transfer admittances. So their definition is pretty simple. So capital Yij basically just a negative lowercase yij. So here I is not equal to j. If you like, you can also define the inverse of this matrix as impedance matrix. If you like to use admittance instead of admittance, that's okay. Then this equation will become this equation. You just replace the y bars by you just multiply both sides by the inverse of the admittance matrix. So original equation can calculate the current directly, right? If you know the y bars and you know the v bars, you can calculate the I bars directly. And this equation can calculate the voltage directly. So which is equal to the current injections at the both buses multiplied by the impedance matrix. Okay, let's come back to this simple example. Let's construct the Y matrix, and also we can try to calculate the Z matrix, the Z bus matrix. All right, so the Y bars is simply just 4x4 square matrix. Diagonal element, each diagonal element will be the sum of the admittance between this bus to all the other buses, including the ground. Let's take a look at how to calculate this one. So this is a capital Y11. Capital Y11 by definition will be the admittance to the ground plus the admittance to bus 2 and to bus 3, then to bus 4, right? So let's say the admittance to the ground will be negative 1j. Admittance to bus 2 and admittance to bus 3. So if you add those three numbers together, so that gives you negative 8.5j. But because there's no direct connection to bus 4, so that's why you don't need to consider any connection to the bus 4. So that's how you come up with this negative 8.5j. Similarly, you can calculate anything else. Let's try another one. Let's try bus 4. This item. This is supposed to be a capital Y44. So first item, we need to consider this one to the ground. But because bus 4 has no source, there's no impedance to the ground. So the first item becomes 0. And the bus 4 only have direct connection to bus 3. So eventually you only need to consider this single admittance. So that is same. All right. For the off diagonal element, that will be pretty simple. If there's a direct connection, you just take the negative value of that admittance. If there's no direct connection, you basically just take 0. So this matrix is symmetric, which means the transpose of matrix is itself. Okay, next let me ask a question. So how many non-zero elements do we have for this bus? So this is a 4-bus system. We have how many non-zero elements? We have 4 by 4, 16 minus 4, right? So we have 12 non-zero elements. 12 items are non-zero. But what if we have n buses, not including the ground, and m branches? How many non-zero elements do we have? So to answer this question, we consider yeah, I just show the answer. So to answer the question, we need to first consider the diagonal elements. So diagonal elements have to be non-zero. It has to connect to something, right? So if there's one bus not connected to any others, we don't need to include that bus to the system. So which means all the buses we consider here are all connected to at least one other bus. So the diagonal elements will be non-zero. Off diagonal elements will depend on how many branches you have. If you have m branches, you'll have m non-zero element. But because this is symmetric, so m will be multiplied by 2. So finally, we have 2m plus n non-zero elements. So if you think about, you have a very large system. N can be very large. If the m is close to n, I have a 1,000 bus system, and the branch number is also around 1,000. So finally, you only have how many non-zero elements? You only have around 3,000 non-zero elements. But for this entire bus, if it's 1,000 times 1,000, right? That's a million elements. You only have 3,000 non-zero elements. So this matrix is pretty. This can be a sparse matrix. But if we calculate its inverse, which is the impedance matrix, every element is non-zero, right? So if you deal with a 1,000 bus system, the impedance matrix will have a million elements you need to deal with. So that's why using the admittance matrix is more convenient, more efficient than using the impedance matrix. So now let's try to solve the power flow for this system. Let's give the voltage for each source. Let's assume that the first source has voltage 1.1, the angle is 0. And second is 1.0 with 0 angle. So let's try to solve the power flow for this case. First, we need to convert each voltage source to a current source. So the first one will inject the constant current as negative 1.1 J, and second is negative 1.25 J. Okay, so if you want to solve the voltage of each of the 4 buses, we take this equation, and the left-hand side will be the voltage vector, and right-hand side will be the impedance matrix, which is this one, multiplied by the current. The current only have 2 non-zero elements. So if you do that calculation, you get this voltage vector. Okay, so we solve the voltage for any other bus. Then using the voltage values, we can calculate power flow, right, for each individual line. So here I need to ask a question. If you take a look at the result, the voltage phasors. So those values are voltage phasor, not magnitude. Because everyone is actually complex number here. But why are those voltage phasors all real? Yeah, just think about this one for a few seconds. So they're all real voltage. There's no angle difference. Right, because E1 and E2 has zero angle. Because E1 and E2 has zero angle, and also the system, why they have zero angle? Because the system has no load. I haven't given it any load. So even we solve this system, that represents a system without any load. So that's why all the voltage will be in the same angle. So if the angle difference is zero, there's really no IT power flowing on any line. Okay, but this is pretty special case. All right, so let me leave the next slides. Next slides we'll talk about the type changing transformer. Yeah, so I will leave this one for next Monday. All right.